I'd like to introduce Prashanth and Sachin, who will be presenting Enhancing Security and Resiliency of SONiC. Prashanth and Sachin, Prashanth is a principal engineer and Sachin is a tech lead at Cisco. Both of them travel from San Jose, California to join us today. This is Prashanth and Sachin's first presentation at NANOG, and it's a pleasure for us to have them. Let's welcome them.
Thank you. Hello, everyone. Very glad to be on this stage. Very excited to see you guys here and appreciate your time and being here to listen to this presentation. My name is Prashanth Buddhala. Me and Sachin are part of the engineering team that works on SONiC, and we are looking at platform security and some of the platform infrastructure pieces at Cisco. So in this session, what we will cover is why is security of low-level components important. We'll dig into some of the details, what has been going on in that area. We'll see how SONiC is performing in that area. We'll see what the current state of SONiC is in the open source and what we are doing to make it better. At the same time, we'll also look at some of the boot resiliency of SONiC as well. Again, the current state of open source and what enhancements we are working through. So low-level boot infrastructure, right? This is a piece that doesn't get enough attention because so far, all of the vendor-specific NOSes, the vendors take care of all of these pieces. You get it in the box and you just deploy it, and anytime you have an issue, it's the vendor's responsibility to take care of it. But when it comes to open source, it's quite different. All of us in the community would need to work together, make sure it's working correctly and is secure enough. Now, talking about why it is hard, the security of these pieces starts off the moment you pick your hardware chips, how the manufacturing is done, how the secure encryption keys are loaded onto the box, and how you make sure the right software is loaded and is actually running in your end network, right? Making sure everything is lining up correctly is not a simple thing, and it's complicated. And any misconfiguration, even slightest design flaws, can result in catastrophic failures, and you don't want to see that if you can, if there is a better way to prevent it ahead of time. And if you're following the news in the last few years, trends have shown that these attacks have become more sophisticated. Firmware and hardware are no longer safe enough. You have to pay attention to that. There are cases where the very low level, very first pieces of software have been compromised, and even supply chains have been hacked where the shipments were intercepted, chipsets were taken off, replaced, and sent to the destination without the actual customer finding out, right? Such cases are reported as well. So it's important that we pay attention to the low-level security. All right. Now, talking about SONiC, SONiC is an open source networking operating system that's been widely deployed, primarily in data centers, right? These locations are very secure, very controlled places. It's okay if you do not have all the pieces taken care of because you are actually deploying them in a very, very, very constricted locations. But if SONiC has to get out of a secure DC location to branch networks, your remote offices, we'll have to pay very close attention to some of the security aspects of SONiC, and that's what we are going to look at today. Given that SONiC is a network operating system, it's going to run on devices that are directly interacting with the external bad actors on the network, and it's very important to make sure it is working well and safely. And it's a high-stakes game, right? If your front-end network that's facing the external world is compromised, protecting things behind it doesn't matter much, because at that point the threat actors are actually can control your network better than you can, right? So making sure network devices are protected is really, really important. And the cost of actually restoring a network that has been compromised is huge, right? You wouldn't want to go that route at all. So some of the key areas that we'll look at is obviously going to be how we'll prevent it first, and if prevention fails, can we detect it, right? So we're going to look at both aspects, and as part of that, we'll examine each of the boot components. We'll look at how the supply chain can be protected in using these areas, and we'll see how the platform identity as well as remote attestation help us get that job done. With that, I want to hand off to Sachin, who will walk us through the details next.
Hi everyone, my name is Sachin, and I'm working at Cisco as a senior tech lead, and I'm fundamentally responsible for focusing on security in the SONiC as well as the platform security. So as my friend mentioned, let me touch a bit upon it. SONiC is an evolving network operating system. What it means that it is going to sit on many routers and switches, start controlling various infrastructures, cloud services, and a different set of network elements, right? The cost involved here huge. So the security becomes a critical functional component for SONiC to protect all these devices and security infrastructure, all of these things, right? So security has to start with somewhere. So the very tiny code, which is well controlled, well known, it has to be started from there, and it is layered across the platform, right? I mean, start with the root of trust, then further go the trust chain to firmware component, then the software component, and then rest of the software modules, right? So this journey we have to start with root of trust. So it becomes very important to implement a security in SONiC. There is a right set of a hardware has to be there. In Cisco, all of these hardware start with a trust anchor module, where the root of trust firmware is pre-programmed and it is immutable. When the power on of this device happens, this tiny immutable code is very first loaded on the CPU, and then it establishes the trust chain on the bootloader and SONiC kernel. So let's understand what is currently exist in SONiC. In this picture, if you see, SONiC is in a Debian distribution. So it leverages the Debian infrastructure wherever possible to implement the security functions. So in the as a Linux Debian distribution, SONiC does support a UP secure boot. What it means, there is a root of trust starts with the BIOS, which is a firmware version, but it's a field upgradable. Then the root of trust, when it booted on the CPU, it is the first SONiC component it is going to load is a shim. Shim is a very tiny code, well known, fundamentally managed by Microsoft, and they authorize or signing, and it is responsible to extend the trust chain from hardware vendor to NOS vendor. So to do that, it provides a certain functionality such as a machine owner key management. Also, it provides some configurations where secure boot can be enabled and disabled if you are the root user, right? So then shim loads the grub. Grub is a generic bootloader. It is initially designed for PC world. Then slowly it is widely adopted in Linux-based systems. Grub provides, since it is designed from the generic purpose. It provides a way where, for example, grub config, where you can provide a various configuration to locate your Linux kernel and initrd, and as well as you can even modify the kernel parameters on boot path. So during the boot, you can interrupt into the grub, either get into the rescue module or fix certain configurations, etc. SONiC is heavily uses this grub as a primary bootloader, and it is responsible to verify the Linux kernel. So then it verifies the initrd. So here these are the very critical component in the boot path, the grub, initrd, SONiC kernel and grub config. The UP secure boot stops here, and since SONiC kernel being in a central critical component for the infrastructure run, the SONiC kernel in a way further establishes extends the trust chain for a kernel drivers and all, right? Every kernel drivers are enforced to be checked its signature before it loads. So this is currently exist in SONiC, but what we announced here for the Cisco platforms, which in a way we are generically announced it, we are going to upstream this one soon. So if you see in the picture, obviously SONiC, to implement the secure boot, we have basically leveraged our platform, which provides a built-in trust anchor module, and anything such as a secure boot key programming, platform identity programming, any initial programming has to be done in the manufacturing and then lock it down. There is no way to modify, unauthorized way to modify these content. So our UP implementation in our trust anchor module, and then we extend this UP secure boot extension in the BIOS. Now from the BIOS, these two pieces are in the trust, builds the trust in the hardware. Right now, trust has to be extended to the software, where actually we leverage what SONiC has, where the BIOS can verify the grub. But here we made a change. In our case, grub config provides becomes a kind of protecting grub config becomes very critical, because it interrupts the boot path, and we wanted to lock down so that there is no edit happens. If you see in this picture, we also removed a shim for the same reason. It provides an ability to enable and disable secure boot and mock management, all these things. We have a different way to do the mock management, right, directly on the root of trust, not in the software. So with that, we remove the shim and extend the grub functionality, where it can verify the grub config. That means we do sign the grub config. And we lock down the grub menus, where control D or whatever it is, you cannot edit anything in this boot path. So now grub is going to load the SONiC kernel, which further verify the SONiC kernel and initrd. In upstream SONiC kernel verification is already supported. We extended this functionality in the grub so that it can even verify the initrd. Initrd is the initial bootstrap code which loads on the memory. Then it establishes the rootfs, root file system on the disk, and rest of the software can start bootstrapping from there. So protecting initrd also becomes a very critical function. So with this solid foundation, we say that all these critical components are allowed to boot only if they are signed and the right set of verification keys are present in our trust anchor module. This is a story of a secure boot, and we are planning to extend, since it's fundamentally provided a baseline of a security on the critical component. Then we were planning to extend these functions in the Docker, as well as the Debian package installation, as well as in the binary. That's our roadmap. Along with the secure boot, which secure boot prevents the any unauthorized software running on the system. It's a prevention technique. And we also need a detection technique where we need to detect what's happening in the device when we are managing the thousands of devices in the operation center. SUDI, which is also called as an IDEV ID in the TPM mode. This is a IEEE 802 standard. So you can these specifications are defined in these RFCs, right? We are adhered to that. What is the SUDI? SUDI is asymmetric key pair, which we enroll during our manufacturing process, which provides a unique identity to the device. These asymmetric key pair, the private and public keys, both are part of the trust anchor module. The private key never leaves the system. If for any attestation reason or signing reason, you can reach out to our trust anchor module to sign the messages or nouns or any data log. The public key is enrolled in a certificate which contains the product identifier information, serial number, as well as the many vendor details. This certificate issued by Cisco public key infrastructure so that anybody cryptographically verify the device identity. So what we did is SONiC here. SONiC basically we provided an agent software which basically interact with our trust anchor module to fetch the SUDI information and hand over this information either locally or a verifier, external verifier, and also allow the signing the any messages which external verifier want to attest. Typically in initial communication, TLS communication, for that these sort of an encryption technique helps. Let's move on another way of verifying the boot history, right? Along with the secure boot, we also enabled in the SONiC and in our boot component that anything which loaded on the CPU, it can be a software, firmware, or it can be some states are measured in the our trust anchor module. Our trust anchor module has a set of predefined registers, which we call it as a platform configuration register. This is as per the TCG guideline. So there are around 24 registers we have currently. Each register carries the group of histories. So PCR 027 is typically meant for the boot integrity, right? So for example, when the switch is power on, the very first software which loaded from the boot ROM get extended by itself, then the BIOS gets extended, then some of the BIOS runtime states that get extended, postcodes that can get extended, then grub config, initrd, and Linux kernel, all these are extended in the PCR 0 to PCR 7, right? So why this is needed? Basically PCR provides an evidence that how the system is booted, right? If there is a verifier wants to verify to how this system is booted, the verifier is going to reach to the SONiC, hey, give me your boot evidence, right? So we have two sort of an evidence. One is the integrative measurement, which are stored in the trust anchor module. Also, while doing this path, we also record the history of this boot load that we call as an event log. Currently in SONiC, what we implemented locally, we validate the event log history compared to the what is there in the trust anchor module. We recompute from the history and generate the final integrative PCR values and compare and see that okay, things are as expected. For a verifier, we have a model that from our manufacturing, we publish our known good values for this SONiC, for this particular hardware and setup firmware. These are the PCR values. It has to be enrolled in the somewhere in the controller or a verifier. Then when the system is onboarded, to the network. After the device identified, the what verifier is going to do is check on all these PCR values to see is this exactly booted as expected. If that happens, then enroll the device on the network, otherwise, reject it. So in a nutshell, what we are saying is, in a SONiC, today we built a secure boot, measured boot, and we provided a fundamental layers where actually the trust chain can be extended further. And we also provided a verifier. Whoever wants to verify, there is a technique, it can reach out to the device, get the evidence, get the platform identity, and all these are cryptographically verified. So with that, let me finish here and hand over to about the SONiC boot resiliences to my friend Prashanth.
Sure. Thank you, Sachin. That was awesome. So just to recap, right, with enhancements that Sachin just talked about, we know how to secure the hardware, we know how to secure manufacturing, we know how to secure the whole pipeline of software. And with all of these enhancements, it gives us more confidence to deploy SONiC, outside a protected, facility like a DC. Now let's talk about resiliency, right? In a DC, traditionally the way SONiC has been doing is you have redundancy at device level, right? If one of the devices malfunctions, there is a equivalent device that takes over immediately and things continue to function, right? That's great, right? But there are a lot of deployment scenarios where this is not really practical. You wouldn't be able to deploy a redundant device in every branch location. That's going to be cost prohibitive, right? If one of the device malfunctions, recovering it, if you have to do a truck roll to a remote destination, that's a no-go at all, right? That's a heavy lift, and it's a network downtime, which many of the networks can't afford, right? So what can we do about it? So what we were looking at is, how can we make SONiC more resilient, where even if one of your operating systems, one version of it fails, there is a redundant operating system that takes over seamlessly no matter what the failure is. So what we did is, we went and examined what is the current state. In the current SONiC deployment scenarios, it is a single disk drive with single partition for all of the essentials that are there. So there's a UFI partition, which is the early boot code. There is an ONI partition, which is the open network install environment, which is needed if you want to reinstall SONiC, right? And there is one single SONiC partition. Now, if your SONiC partition malfunctions, you have to boot ONI, which is a separate operating system by itself. It is a full-fledged Linux operating system that brings in tools that will allow you to install a new SONiC version, right? So there are two distributions of Linux on that machine. Now, if somebody is deploying one operating system, we all know how hard it is to protect it, let alone two of them, right? So that's something we were looking very closely to enhance so that we can probably do a better job and make a more resilient SONiC operating system. So what did we do about it? We went ahead and made duplicate partitions for all of the essential pieces, right? So there's AB partitions that are needed for each of the essential pieces, which is the UFI, and for SONiC as well. We, of course, have a data partitions, which are, again, AB as well, if applications need storage space that needs to be resilient as well. Now, how does these multiple partitions help? Each of these essential partitions, be it the EFI or ImageA, are completely independent. They can be loaded from either of them. So EFI A gets corrupted, EFI B takes over. And if image A is corrupted, image B takes over. And all of these pieces work with each other to figure out what the next partition that should be used if one of the primary partitions fails. How did we do that? This is a quick overview of the image pointers that are out there. We have, On most of our Cisco devices, we have BIOS, which is the regular primary BIOS. There's a golden BIOS as a backup. If the primary BIOS fails, golden takes over, right? And similarly, we have a primary EFI A partition, and there's a EFI B partition. And then again, obviously, there are SONiC partitions as well. So the vertical down arrows are the primary paths that are taken, right? And if any of those vertical down arrows fails to figure out the next partition that needs to be used, it automatically falls back to the redundant partition on the other partition, essentially. Now, how does this eventually end up with the right version of SONiC? That decision is actually in the grub configuration, which is again hosted on both image A and image B partition. And that grub configuration determines what the user really wanted, whether they wanted SONiC A to be their primary or SONiC B to be their primary. And those two grub configurations are kept in sync anytime the user comes and changes, what should boot next. All right. This is just a description of how the boot sequence works. Primarily, again, you have a USB disk and iPXE, the default boot options on there. If a disk is chosen, we have configured EFI A and B as the primary ones in there. If EFI A fails, B takes over, kind of, right? And grub, as soon as EFI exits and grub starts off, at that point, grub is primarily in charge of making sure the system is booting. Today, grub has a way to fall back if one of the kernels that's configured in its configuration doesn't work, right? So if it goes through its menu options where, first option, second option. So when it detects a good kernel in its first option, it tries to boot that. And if it fails, we have configured the fallback, which is the next partition to detect. Now, grub can detect if the kernel is valid or not by checking some of the signatures. And once the control jumps into the kernel, at that point, grub is out of the picture. The fallback option no longer works. Now we are in the Linux kernel itself. Now again, there are so many things that can go wrong in Linux kernel initialization. And if you upgraded your Linux, I'm sure you would have encountered where if one wrong setting in there can cause the whole kernel to hang, and grub will not help you there. Every time grub will go back and boot the same kernel, and you'll probably be stuck. And that's the current state in SONiC. So what we did there is we went and changed that, where we initially, as soon as the very first piece of code executes in the kernel, we set the next boot as the backup kernel, and only when the whole initialization succeeds and all of your services are up and running correctly is when we reset and make sure the next boot is set to the right kernel again. So that's the enhancement we did. So we are running short on time. So this is what we are planning for future work, right? Obviously, security is a continuous effort. We are going to continuously try to look at all the enhancements that are still required. We have listed some of the root file system enhancements, integrity checks that we want to add in the multiple disk support. There's a PR open for the HLD for boot resiliency. You could go back on in there and take a look. Yeah, feedback is welcome. We would want to work with you to see if there is more requirements in there. Yeah, that's about it. Thank you. Hopefully we have time for a few questions.
Hi, I'm Mark Austin. I'm CEO and founder of Hedgehog. Previously at Cisco, where I had the opportunity to work on Cisco Crossword Trust Insights, which does attestation for iOS XR devices. So my question is, for the trust attestation that you presented today, will that be supported in Trust Insights for attestation reporting?
So yeah, it's not automatic at this time. We are working on it. The way we implement it right now is in our CI/CD pipeline. When we build an image, we have a predefined firmware set. All those hashes are part of the build part, and At the end of the CI/CD pipeline, we load the image onto the router and collect this snapshot, and we basically right now host into the some artifactory. We wanted to host it in the CCO, but that's not approved yet. But we host it in some artifactory. Then we have our counterpart controller T, which basically downloads based on the SONiC version these artifacts, and actually they are re-signing with their cloud keys, then import into the controller. That's how it is.
Great, thank you.
Hi, we have a remote question from Manish Parmar. So the question is, which vendor uses SONiC software?
Sorry, could you repeat that?
Which vendor uses SONiC software?
So which vendor is SONiC software from? Is that the question?
Which vendor is using the SONiC?
I mean, there are many device vendors that support SONiC today, right? I mean, the list is out on on SONiC's webpage right now. Cisco supports it. I'm sure there are many others as well. A few others that actively support, and they are being deployed actively in production data centers today.
Thank you.
Please be brief.
Good afternoon, Dan Curiano. So I've been running SONiC for the owning for the better part of the last decade. I'm just curious, do you have any rough idea of what ratio of platforms actually support dual EFI? And second question to that is, how do you fail to the second separate partition? Do you have any mechanisms in place to go from one to the other should one fail? Or is this still left up to the user through out-of-band?
So second question first, I think I understand that clearly. So we have changes in BIOS where we go try to detect which EFI is correct and is readable properly. And if that read fails, we automatically switch over to the next one. Right? And this is controlled in two ways. One is a small BIOS change, and the other one is the EFI boot manager settings, where we order these correctly in the list so that it checks each one right after the first one. If you don't mind, if you could repeat.
Yeah, second one in Cisco, it's a mandatory for us to every hardware to support secure boot. But we have in the SONiC we kept as in a knob. But if the non-secure boot supported firmware, they can just disable that in the build configuration and build an unsigned SONiC by themselves.
Okay. Yeah, you mentioned in Cisco. What about the white box space? What's the landscape for dual UFA BIOS? Is that pretty prevalent? Is that pretty common? Do you have any idea of what the proliferation is?
No, I have no idea on that.
Maybe you guys can continue the discussion offline.
Yeah, I'll be offline there. We could absolutely chat.
Thank you.
Thank you for the wonderful presentation.
Thank you.